So we've been discussing in previous videos doing integration by substitution in order to undo the chain rule. There are some antiderivatives where there is a U substitution involved, but it's not a very obvious one. And they kind of fall into two scenarios. The first of these is when we're dealing with inverse trig involvement in antiderivatives. So for example here, 1 over x squared minus 2x plus 2, and I want its antiderivative. This is a multiple choice. You could just take the derivative of each of these and see which one gives you a simplified derivative of what we're starting with. But if I wanted to find this directly, what I'm being asked for is for the integral of 1 over x squared minus 2x plus 2. And this is not a very obvious scenario because I'd be thinking, well, if this is U substitution, and I say U is the bottom of my fraction, well, that means when I find du dx, I should see somewhere a 2x minus 2 to cancel out when I substitute in my dx and change it into du's. But I don't see that, so this isn't going to work for us. What we actually need to do is we need to do completing the square. If we complete the square with this, completing the square says I want to make this into a perfect square. So I want to take the x squared minus 2x, and I want to know what would go here, and I'll have the plus 2 here, but what goes here to make this part a perfect square? Well, the way we do this is we take this part, and I'm going to divide by 2 and make that whole thing negative. It's the negative b over a. Oh, I'm sorry, negative b over 2a type idea from the quadratic formula, which would mean this would be plus 1. Well, that means that I now have x minus 1 squared. I have this plus 2, but I just added a 1 in here, so this orange is no longer the equivalent, the same as orange and green together. So I need to cancel the plus 1 here by subtracting 1 here. So when I do that, I now have x minus 1 squared plus 1. So here, this is now the integral of 1 over the quantity x minus 1 squared plus 1 with respect to x. And this now looks a little bit more like a case of chain rule, where I see, well, x minus 1 is inside of my bigger function of that fraction, which means du dx is equal to 1, which means dx is equal to du. So I now have the integral of 1 over u squared plus 1 du, and this has an antiderivative of the inverse tangent, u plus c, because I'm writing it as an indefinite. And then changing back to u's, I have the inverse tangent, x minus 1 plus c, which, because they just ask for an antiderivative, that means c could be any constant. That makes it our answer E. As if completing the square weren't challenging enough with this, the other scenario we have to deal with is something that looks so close to inverse tangent to begin with. And it's a case of I have a constant on top. I'm adding here, and what I'm adding are perfect squares. We have to do a U substitution in order to make this be the antiderivative of, or make this be the derivative of inverse tangent. And what it is it'd be really nice if this had something involving a 64 in it. Well, there are a couple ways of thinking of it. for some people, it's the idea that, well, instead of saying u equals something, I'm going to say x equals something. X is going to be the square root of this number here, the 64, times u. So that way, when I do my substitution, I'm going to have 1 over 8x all squared plus 64. Now here, I can take the derivative of x with respect to u, which would be 8. So dx is equal to 8 du, so times 8 du. Simplifying this, I have the integral of 8 over 64x squared plus 64 du. Oops, not dx, not 64x squared, 64u squared. I can factor out an 8 on the top. I can factor out a 64 on the bottom. So I have 8 over 64 times the integral of 1 over u squared plus 1 du, which now gives me the antiderivative being inverse tangent of u plus c. But then I have to replace the u. Well, I said x equals 8u, which means that 1/8 x is equal to u. So I have 1/8 inverse tangent of 1/8 x plus c.